All right, let's start on time. Today, we're going to talk more about single cycle microprocessor. And before that, let me quickly talk about Prelim 2. Okay. It's going to be scheduled on Tuesday, April 20th. Again, it's going to be in class, right, at 1 p.m. And this time, we'll do an 80-minute exam. Okay, last time we did a 75-minute exam. And the coverage is going to be from lectures 8. Okay, lecture 8 through lecture 16, including today's lecture, right? Same protocol, same exam protocol, same Zoom link. Okay, just like last time, open book, open notes, and we are going to release a sample exam later tonight. We'll also schedule a TA-led review session, most likely next Thursday, on April 15th at 8 p.m. Eastern Time. Lisa is going to make a post on the Piazza to confirm. If you have any schedule conflict, let me know, or just send an email to 2300 staff right away. Okay, I'll give you guys a bit more detail about this prelim maybe next time. But just like the last time, right, like prelim 1, everything's going to happen on Zoom. We're going to be using item pool. Right? You need to basically turn on your camera. Right? Any questions about prelim 2? Okay. All right, so let's continue. Let's do a quick recap of what we discussed right last time. We talked about this so-called single cycle microprocessor. Right, we have this ALU, right, which is reading this operands data from so-called RF register file, and we may or may not write to this main memory RAM. And also there's the control unit that generates so-called control words. Right. At the end of last lecture, we talked about these instructions. Right, these are the examples. If you look at the first one, this is really arithmetic, right? We're doing addition here. Just want to make it clear here. I'm highlighting the information flow or data flow through this microprocessor. Okay, basically the lines right over here. There's heavy lines in green. This is the data flow that this is basically how the data will flow for this specific instruction when you're doing addition. Right? Again, we read out from the register file. Remember that we have 3 concurrent ports, right? We have 2 read ports and 1 write ports. We can do 2 reads and 1 write at each clock cycle. That's what we have. That's what we offer with RF. And with this instruction, we don't really need to interact with the RAM, right? So that's where we take this pass, we call it ALU pass, and this is where we set MD, right? Over here, we set MD to be 0. We take the upper pass and we write it back, right? We write it back to RF. So that's where we set LD. Of course, we need to set the correct addresses, right? SA, SB, and DR. And we also need to set this load basically load enable or write enable for the RF. Okay, so this is the first instruction. Just want to give you a heads up, right? So there will be a quiz pretty soon. If you have any questions, let me know. Okay. Right. So there's a question. Almost asking the address DR. Right. What is this? Basically, yes. So this indicates the index of the register that we are writing to. We are going to be writing the value, right, on this D inside to that register DR, indexed by DR. All the registers inside RF, they are indexed. Right? That's how we can address them. Over here, we are assuming that we have 8 registers in RF. That's where we are using 3-bit address. Okay. And also later on, the assumption is that in our RF, we have 16-bit register. So that's the width of the data. Okay, so this is the first instruction. Second one, what is the instruction? What's the type of this instruction, the second one? There's a name for this. Store, very good. Is it store? Are we writing to the, it's good that you guys remember this instruction, right? Which one is the store? The third one is the store, right? The second one is a load. So pay attention to who are we reading and who are we writing to, right? So we are actually writing from memory over here. M means the main memory. So this is actually a load. we actually load into the RF, right? In this case, DR is R1. The destination register is R1. So this is actually load. And if you look at this instruction, we are taking, so this is how the information or how the data flow, right? How come I have two colors here with these heavy lines? Any ideas? Why do we have two colors here? Why do I use this kind of color code? What's going on with this purple lines? Right, very good. Right, you know, we are trying to make use of this path, right? So because really over here, you know, we have this so-called base address, right? Base address is specified by the R2, right? This register, and the offset. The offset is 0, which is encoded in this IMM or immediate field over here. But what else, right? Any high-level explanation why do I have this color code? Why do we have this two kind of heavy lines? There's actually a distinction. Very good. Okay, excellent. So there's over here. See here, we are doing a load, right? We need to compute. We need to calculate a memory address. M address is the memory address. This is where we use the ALU for. Right? We use ALU to compute base plus offset. That's how we get the address. Once we have the address, we can get the data out. This is the real data, the actual data that we are writing back to the RF. So over here, I'm using the purple line to indicate the address, right? And we are using the green line to indicate the actual data. Right, third one, this is a store, right? We just discussed. This is actually store. This is where we are actually writing to the same memory address, but in this case, we want to put the value in R0 to the specific location specified by R2. Okay, R2 is the address. Again, the offset is 0 here. Right? That's where we have, you know, we'll put 0 here in the immediate field. This is my control word, right? Make sure that you guys are familiar with this, right? You guys really need to practice, and there will be a quiz right after the slide, I think. Okay, this is where you guys should ask questions. And one thing that you need to pay attention is for store, right? For store, we have something called MW. MW is a memory write enable. If it's 1, then we are writing to the memory. So that's where MW is 1. Okay, and also we don't really care about the write back pass, right? Over here, because we are writing to the main memory. So this pass is not really useful. This is where MD is a don't care. Okay, over here, MD is a don't care. And also DR, right? This is don't care. Okay. There are some questions. What happens if IMM is not 0? Okay, let's say IMM is 4 here, the question. So that means we are writing to this, right? R2 plus 4. This is the address. Is it clear? Okay. Basically, over here we are just using a special case. The offset is 0. And there's another question. Amanda's asking, can load and MW both be 1? Very good question. We actually talked about this briefly last time. Right? In our 2300 microprocessor, right, in our architecture, we don't allow that. We don't. This is actually not something that our instruction can support. We don't allow to write something, right, both to memory and registrar. Actually, in most architectures, this is not allowed. But this is a good question. Okay. Usually, we either write to the memory or we write back to the RF. All right. Any more questions? Now we just talked about doing addition, right? Actually, last lecture we talked about quite a few different things, right? One thing is we want to do this, right? This expression, right? We already know how to do add. We already know how to do sub. We also know how to add an immediate, right? Add a constant, and you guys just practice that, right? There you're doing subtraction instead. But how about this one? So how about multiplication. We haven't talked about this yet. In fact, you can probably imagine that multiplication is more expensive, right, in hardware. There's actually a good chapter and section in the book that tells you how to do different kind of applications, including how to do so-called parallel multiplication. This is not something that we're going to cover in this class. Instead, we'll focus on something called sequential or iterative multiplication. So basically, in our ALU, we only support add, sub, and some logic operation and shift. And I'm going to show you soon so how to use this add and shift. Let's just use this as basic operations to perform the multiplication. Basically, we are doing something like soft multiplication. We don't have a real multiplier in hardware. Okay, we are going to do so-called iterative multiplication. But first, let's see how do we actually do the multiplication in a binary format. Right? Let's just focus on the unsigned multiplication. So for now, let's just assume that all the numbers are unsigned, not in 2C format, not in 2's complement, right? Actually, the 2C multiplication is slightly more complicated, but the gist, so the essence is pretty much the same. Okay. All right, so let's do a very simple one. 5 times 3. Okay. Again, this unsigned, right? 5 is 101, 3 is 011. The way we do multiplication is actually very similar to this decimal multiplication when we have multiple digits. Essentially, we just try to compute the partial products, right? Just like how we do the decimal ones, and then we just add them up. Okay. In case this is not really clear to you, right? What's going on? Let me try to break it down a bit, right, for you guys. Okay, we're doing this, right? 5 times 3. And this is really the same with, right? We can decompose 3 into this, right? Let's just do this. They're the same, right? Agree? And also, we already learned that. First, we can just distribute and multiply. Right? We already learned that if we multiply by a power of 2, really this is a power of 2, right? This is just 0, which is not too useful, and this is also power of 2, right? 1 is power of 2 to 0, and this one is power of 2, just a 2 to the 1. This is equivalent to a shift, right? Okay. Then everything else is just straightforward. Right? We just distribute, and then we get 0. We multiply by 2. That's just a shift, right? We just need to append a 0. Then we multiply by 1, no shift, right? Same thing. That's how we get this partial product, right? See here, this is the leftmost one, and this is a shifted version of this multiplicand 5, right? This is the second one, right? And this is a 0. And we just add them up. That's it. Okay, hopefully this is clear, right? Essentially, the partial products are just the shifted version of the multiplicand. I'm going to call this A and call this B, right? I'm going to call this A as the multiplicand and the multiplier as the B. Really, we are just adding up a several shifted version of the A, right? Of this A value. That's it, depending on the corresponding position in B. Emily is asking, is that considered to have overflow since the result is more bits than the numbers being multiplied? Excellent question, Emily. Right. Over here, we just assume that there's no overflow. Right. Again, that depends on the actual bit width. Right. Now, if we have, let's say we have 16 bits in our register, indeed, in some cases, right, if you're not too careful, we will overflow. And that's something that the software has to take care of, right? Because the software can decompose a wider multiply into a sequence of narrower multiplies. But indeed, so when we do multiply, usually we will have to double the bit width, right? So that's where overflow may happen, right? If you're not careful. Any questions about this one, this example? Okay. Really, it's just about the partial products, right? and the partial product is basically a shifted version of A. If you get this, then you pretty much appreciate the essence of the binary multiplication. Okay? And this is a more generalized example. Again, I'm assuming that I have 3 bits here. Okay, 3 bits here. And the first partial product, right, is basically like this. Okay. Again, depending on whether B0 is 0 or 1, right? This whole thing, if B0 is 0, then the whole thing is 0. Otherwise, just A. Second partial product, so we look at B1. Okay. Again, we shift A to the left by 1 bit. So really, we are just appending a 0 here. Okay. And if B1 is 1, then we count, right? We are going to add this partial product. Otherwise, we skip. Same thing for the third row, right? We append 2 zeros because we are now looking at B2, right? B2 has a higher weight. If B2 is 1, then we add this partial product. Otherwise, it's a 0. Okay, as simple as this. So this is how multiply works in binary. Okay, so let's try to translate this process. Okay, this is a sort of human readable process into something called pseudocode, basically into a program that the computer can understand. Let's just first use a descriptive version first. Okay, and here are my assumptions. First, I assume that A and B, both multiplicand and multiplier, they are initially stored in memory. We actually need to load them into the register. And P, the partial, actually I'm going to use P for both partial product and the final product. So it will be stored into the memory. Okay, it will be stored back to the memory at the end. So that's what we want to accomplish. Okay, and let's see how we can write down the pseudocode. Right. What we want to do is first assume that we have this A in this specific memory location. Absolute address memory 0. Okay, this is 0. This is absolute address. Okay, and this is a typo. I'm going to fix this. No more B here. Okay, and B is in M1, address 1. We load it. We load A to R1. We load B to R2. Then we associate R3. So we use R3 for P. P is the product. And we're going to use it same register for partial product as well. This is an iterative process. What we're going to do is we will just do this row by row. Okay, I'm going to just do this in this way, row by row. And for each row here, we update the partial product. Okay? Basically, update the final product. We calculate partial product and we add it to the final product. That's the game. That's our game plan. Okay, so that's why we have a loop. So this is really a loop. This is a so-called iterative multiplication, right? So that's where we actually need to go through a few iterations. So how many iterations do we go through? That actually depends on how many ones. So this is actually data dependent. Depends on how many ones do we have in the B. Depends on the actual value in the B, not exactly the number of ones. Okay, here. So first, when we enter the loop, we first check, right? This one, LSB of B. LSB means the least significant bit, right? When we enter loop, basically we first check B0, right? This is the LSB. B0. If B0 is 1, we add A to P. Right? A is basically the partial product. We add A to the final product. So that's it, right? And then we ship right. We ship B, sorry. We ship B to the right. Okay. By 1 bit. Why do we do that? Can you guess? Why do we ship B to the right? Very good, Jacob, right? Because next time, right, we just look at B0, right? Just look at B0, and then we already add the same. Again, depending on whether B0 is 1 or 0. If it's a 0, we skip, right? We don't add. That's why we have the if statement. We have an if here, right? If B0 is a 1, we add A. Next time, we want to check B1, right? So that's where we want to shift B to the right, so that B1 becomes the LSB. B1 becomes the least significant bit. Is it clear? Also, we want to ship A, right? We want to ship A to the left by 1 bit because we want to get this is the second row now, right? You want to get the shifted version of A. This is the next partial product, right? And then we just repeat this process. Okay? Next time, in the next iteration, okay, if the whole thing, if B becomes 0, then we skip. Otherwise, we look at B2, right? And we add the shifted version of A. Any questions about the pseudocode? Is it clear enough? Eventually, after we are done with this loop, we store R3, which is P, okay, into this memory address, M2. Okay, so this is the sort of distributed version. This is a more readable version of this algorithm. Right? This is really an algorithm. Right? We are doing this multiplication in an iterative fashion. And the cool thing about this one is that we are not really doing any real multiplications. Instead, we just do add, addition, shift right, and shift left, right? And also we need to figure out how to check LSB. Okay, we actually need to figure out a way to use our current instructions, our operation in the ALU to check LSB. So how exactly do we do that? This is one question, right, that we have. We want to check LSB. Okay. All right, so let's try to further refine this pseudocode. Now I'm using a more program-like, right, description. This is a refined pseudocode. First, I'm loading M0 to R1, M1 to R2, and I initialize R3, which is P, the product, with 0. Then I enter this loop, marked by this star label. Okay, mark this label. This is the start of the loop. And this is how I check LSB. Okay. So I'm doing first again R2, right? R2 is read B. Okay. R2 stores holds B. What I'm doing here is I'm doing an AND. So this operator means AND, okay, in my pseudocode. I'm ANDing R2 with the 1. What does this mean? Okay. Over here, I'm assuming that we have 3 bits, right? For both A and B. So really what I'm doing here is I'm ANDing B2, B0. I'm doing this bitwise AND with 0, 0, 1, which is 1, right? And that's how I can get what's the end result after this AND. If I do bitwise AND for each bit position. Very good. 0, 0, B, 0. Make sense? I'm doing B0 and 1, right? 1 is the identity element for AND operation. So that's where I get B0. That's how I can extract the LSB. Is it clear? So basically now R4 holds the LSB. All I need to check is if B0 is 1, then this statement, right, this if statement, will execute the addition. Right? Over here, I'm just checking whether R4 is a 1 or not. R4 now holds this value, 0, 0, B0. Okay. If B0 is a 0, then I'm skipping the addition. Otherwise, I'm adding R1, which is A, or the shifted version of A to the partial product, okay, or the final product. They're the same. After that, I shift, right? I shift B to the right. We already agree on that. And I shift A to the left. Okay, so I get the shifted version, which is the partial product, the next partial product, right? And I continue. This is where I check whether the whole B, so the shifted B, is already a 0 or not. If it's already 0, then there's no point to continue, right? There's nothing to add. Otherwise, I go back. Okay. And I continue this iteration. This is why it is called the iterative multiplication. Right. Eventually, we write back. Okay, R3 now holds the final product. Okay, hopefully this is clear enough, right? If this is not still not too clear, let's just do a quick exercise, just to make sure that everyone's on the same page. All right. Now, let's just look at this example that I've already showed. We are doing A with 5 times 3. Right? A is 101, unsigned, right? B is 011. Let's try to fill out this table. Assuming that the iteration. So I'm basically doing this, right? So this is how we evolve the iterations, right? This is from the iteration 0, 1, 2. I want to let's just work together on this, right? So let's fill out this table. Let's fill out the value per iteration. This is basically iteration 0, 1, 2. Okay. Let's see initially, right? Iteration 0 means initially what are the values in these registers? Okay, what is R1? R1 holds A. Right? What's R1 initially? It's 101, right? R2 is 011, right? R3 is initialized with a 0 here, right? Okay, and R4, what is R4? So the first time we compute R4, what's R4? Right, R4 is just a 1 or 001, right? Doesn't matter. Actually, over here, I'm assuming that all the registers have 16 bits. I'm not going to show you the zeros here, right? We append 0 on the left. Agree? Right, so this is the initial condition. Okay, so next time, what is R4? Let's look at R4. In the next iteration, okay, we go back, right? What is B1, right? So basically we are checking B1. So the LSB of, right, the shifted B. So it's still 1, agree? R3, what is R3? R3 is P next time. Oh, actually, let me, just to let me be clear. So since I actually only have 3 rows, maybe let's try to cut corner here. Okay, so we have, after we execute our we got R4, which is right a whole here. This is 001, right? Let's update R3 in the first row, the very first row, iteration 0. So R3 it should be the same as A, right? Agree? Right, in iteration 0, R3 is already updated. Let's say it's already added. Otherwise, I'm gonna run out of rows. Okay. Next time, we already agree, right? R4 is still a 1. And what is the updated R3? Do we update R3 or not next time? Yes or no? Yes, right? Okay, basically we do 101 plus the shifted version of, right? Okay, the shifted version of A, which is 1111. Okay, let's just focus on this too. Make sense? Right? And next iteration was R4. Next iteration. Of course, this thing will be shifted, right? So R2 will be shifted correspondingly, right? Hit to the right, and R1 will be shifted correspondingly, right? To the left. Next one, R4 is going to be 0, right? 0, and we don't add, right? 1111. Okay, and we don't add, and we are done actually. This B will be 0. So this is where B will be shifted to 0. And we check over here, right? R2 is B. When B 0, we exit the loop and come here. All right. Any questions about this one? About iterative multiplication? It's a pretty cool algorithm, right? Okay, fairly short, but it does something pretty powerful, which is multiplication. Okay, Shiba is asking, how are we getting the value of R4? right? So let's just take one more look at this, right? Let's erase this. Erase this. Okay, again, let's just start from the beginning, right? At the beginning, so we know R2 is assigned 0, 1, 1, right? This is where R2 is 0, 1, 1. What we want to get is the LSB, right? The least significant bit of R2 or B. So what we are doing is 0, 1, 1 and 1. Really, 1 here is 0, 0, 1, right? So what we get is you do, let me put it here, right? 0, 0, 1, 1 and 0, 0, 1, bitwise AND. Of course, we get 1, right? 0, 0, 1, we get a 1. That's how we get R4. Okay, this is R2. Is it clear? Yes, R4 is basically the LSD. We want to extract, we want to use this AND. This is actually so-called a mask. So we actually use this a lot in software program as well. We're doing so-called masking. We use the AND to do masking. We mask out everything else. We only keep the LSD. Why isn't it, what does N1 mean? All right, Lauren, yeah, again, good question. So N1 means, like I said, right? Over here, we are doing everything's unsigned. Okay, and of course, this is a positive one, right? Whether there's unsigned or two's complement, we need to append 0, right? Not all ones. Is it clear? 1 means 0, 0, 1, or a bunch of 0 before 1. This is not -1. All right. Okay, if this is clear, maybe it's time to ask a bonus question. Right? Again, if you guys forget, right? Bonus means with a bonus question, if you get it right, you can get 1 extra slip day on an additional assignment, right? Not just 2 assignment. You can get it. You can apply it to the 3rd assignment. And also the other way to get a bonus day or a slip day is to write a review for the Verilog tutorial. Some of you already did, and the review looked very good, very helpful. Okay. All right, so let me ask you guys this question. So now let's try to translate some of this into the instructions that we have already learned, right? Let's try to map this pseudocode. We want to map the pseudocode into the microprocessors, right? The single cycle microprocessor that we have. Okay, so first one, of course, the first instruction we want to map is this load, right? This is load, agree? This is load. But somehow, we actually want to address this absolute address, right? This is 0. Okay, this is absolute address 0. Think about our instruction format, right? We always have something like this, right? We have a base address specified in R, and we have this offset, right? Of course, offset needs to be 0. But how can we make this whole thing a 0? What do we do? How can we make an absolute address 0 using the instructions that we have learned? Is the question clear? Right, so that's my bonus question. First, if the question is not clear, then ask now, right? Otherwise, I'm gonna give you guys a few seconds. Can you repeat? Repeat what, Steve? First, here's a hint, right? You can do more than 1 instructions to achieve this load. Okay. Oh, the question is not good. Okay, the question is not clear. So really, we want to load from this address, right? M0, actually same thing for M1. But let's just focus on M0 here, right? But we need to do a load, right? But with the load that we have learned so far, right? This is the format, right? We have to specify a base, and we have to specify offset, right? To load from a specific memory address. And we want to make sure that our plus 0, the offset, right, equals 0, right? That's what we want to achieve, so that the whole address becomes 0. Really, my question is, how can you create a 0 for R? How can you put a 0 into a register? That's my question. Let me make it a lot more clear. What instruction do you use? How can you make a 0? How can you put in a 0 to any register? Okay, here's my, don't put in the chat window, guys. Let me do the countdown. Now the question's clear, right? Okay. All right, let me just do the countdown. 5, 4, 3, 2, 1. Go for it. Raise your hand if you have an answer. Okay, Jacob, you're the first.
You just take any register and add it to the immediate value 0 and then store it into.
Can you do add? So what do you add? You add what?
Immediate 0.
Right, but add to what? Add to what register?
Just wanted, you could do any register to initialize it to 0, right?
Right, but the question, how do we initialize a register with the 0?
Like for example, R3, you add what's already in R3, you end that with 0.
Okay,
and then you start back in R3.
How do we implement this line? I haven't got to this line yet. How do you implement this line? This is really the gist of the question. How do we map this line into an instruction? Maybe let me ask another student. Amanda?
I was gonna say you would initialize R1 to 0. You could do like R1 goes to R1 minus R1, and then you would use that value to get the index of M, like to get M0, because then that value would be 0, because when you subtract something from itself.
Very good. Okay. Is it clear, guys? Okay. And this is our instruction set, right? Basically, you know, we don't really have a instruction that assigns 0 to the register. So that's why we are doing a subtraction. Okay. Right. So Jacob also made a very good point, right? Basically, we just have to do, right? Once we have a 0, then we add, right? So we basically use that register as a base address. All right, it's not too clear. Okay, and this is the complete instruction sequence. Actually, the answer is already in the next line, right? That's how we make a 0. Okay. I actually intentionally chose R0 because in some instruction set, R0 is used to hold 0. Okay, but not in our 2300 instruction set. Ours is a much simpler, and this is basically how we can make a 0. Right. So later on, when you see this, right, don't be surprised. It's not like we are doing useless work. This is really how we initialize one register. Okay. Once we have this, then we can get the absolute address, right? So this is basically M1, this is M0, right? And we continue. So the rest becomes pretty straightforward. And this is a even more refined pseudocode. Okay. Yeah, Lauren, great point. Yes, you can. Lauren's basically, can we do this? Okay, yes. Okay, same thing. We also get a 0. Very good point. Okay. And this is the complete, right? The control sequence or control words. You just have to execute these instructions. Although we cannot just execute them right one line at a time, because there are some loops, right? We need to jump back at a certain point. Also, we need to make branches. One way to really implement this control unit is to leverage something that we have already learned. Right? We can just write out an FSM, right? So basically, that's why I have this state numbers. So basically, in each state, this is basically the script name for the state. And if I implement more machine, then this is basically output. Right? You guys are basically doing something similar for lab 3. Right there, you actually output a lot of things from each state. We can just do this, right? And then we reset machine, and then we go from 1, 2, 3, 4, and we take some branches, right? Branch out here, and we loop back here in this FSM, right? This is very straightforward. But the downside of this FSM is this is hot wire, right? Basically, you know, for each different kind of algorithm, let's say in this case, we are doing an iterative multiplication, but I want to do iterative division. I also have to implement another FSM, right? For any kind of algorithm, I need to implement FSM. This is just not feasible, right? We actually want our microprocessor to be more programmable, to be able to handle different tasks, right? Different algorithms. This is where we want to have a so-called programmable control unit.